Acid, bases, and pH scale. Acids. pH of 0 negative less than 7. Reacts with methods and bases. Tend to taste sour. Give or contribute hydrogen ion into a solution. The example of this is hydrogen ion plus chloride is equals to hydrogen chloride. AQ stands for aqueous, which means it is a solution in which the solvent is water, dissolved in water.
Bases. pH of greater than 7 to 14, do not react with metals, reacts with acids, tend to taste bitter, give off or contribute hydroxide ions to a solution. For example, sodium plus hydroxide results to a chemical compound, sodium hydroxide. Neutral. pH of 7, neither acidic nor basic. Pure water. Neutralization. We can neutralize an acid with a base or neutralize a base with an acid. For example, there are bases secreted in our intestines that neutralizes the acid from our stomach.
The pH scale, a scale developed in order to determine how acidic or basic a substance is. Values of the scale range from 0 to 14. 0 is the most acidic and 14 is the most basic.
Indicator, a substance that changes color in the presence of an acid or base. Examples, cabbage juice and litmus paper.
For a better understanding, let us watch this video.
He knows a lot about the science stuff, Professor Dave explains.
When a strong acid or base reacts with water, we can say that it completely ionizes, or that every molecule of acid will transfer its acidic proton to a water molecule. If every molecule reacts to completion, this makes things neat and tidy. But when weak acids and bases react, they only partially ionize, and they establish an equilibrium between the ionized and unionized form. And that means we have to do some math. Ka is the acid ionization constant. This is derived just like we got Kc for generic chemical equilibria. Note that we don't include water as it's a pure liquid. In this way, Ka is a measure of how thoroughly an acid-base reaction proceeds in the forward direction. A larger Ka means more products and a stronger acid. A smaller Ka means more reactants and a weaker acid. So an acid with a larger Ka will be more acidic and therefore associated with a lower pH. We can determine Ka experimentally. Let's say we want to know the Ka for a weak acid like phenol. We can set up an icebox just like the kind we already know. We can use the pH to calculate hydronium concentration and therefore also the concentration of the conjugate base, since they are the same. As it happens, the change in initial concentration of the acid is so small that it's negligible, and we treat things as though none got used up. Plug these values into the expression and solve for Ka. From this information, we can also calculate the degree of ionization, which is the ratio of ionized to unionized acid molecules in solution, or the percent ionization, which is the same thing but expressed as a percentage. This is a pretty weak acid considering so few molecules transferred a proton to a water molecule. Sometimes, like in the previous example, the acid is so weak that we pretend the concentration of the acid doesn't change. But if it's a little stronger than that, we can't make that simplifying assumption, and the math gets trickier, but still essentially the same. We can make iceboxes for weak bases as well, or multiple iceboxes for polyprotic acids, one per ionization, just more math. A buffer is a solution that has the ability to resist changes in pH when limited amounts of acid or base are added to it. Buffers are made by combining a weak acid or base with its conjugate. In such a solution, because both the acid and conjugate base are present, they are able to neutralize small amounts of any acid or base that are added to the solution. Many biological fluids are buffer solutions because they must maintain a steady pH to avoid loss of critical biological function. The bloodstream, for example, maintains a pH of around 7.4. Otherwise, its capacity to carry oxygen around the body would be lost. Buffer solutions of a particular pH can be prepared using the Henderson-Hasselbalch equation. We know about pH, and pKa is similar in that if pH is the negative log of the hydronium concentration, pKa is the negative log of the Ka for that acid. What this shows us is that in order to create a buffer solution of a desired pH, we must use an acid conjugate base pair where the Ka is approximately equal to the desired hydronium concentration, or rather where the pKa is equal to the pH. Let's check comprehension.
Acid, bases, and pH. What is acid? Substance that donates hydrogen ions to form hydronium ions.
In water, the O atom contains 2 ion pairs of electrons after completing its octet. The hydrogen ion accepts 1 ion pair of electrons of the oxygen atom, a water molecule, leading to the formation of a coordinate bond. Formation of hydroxyl ion. The hydroxyl ion or hydroxide ion is OH negative. It is formed when 1 hydrogen ion, H+, is removed from the water molecule. When H+ is removed from water molecule, the shared pair of electron remains with oxygen, as oxygen is more electronegative and thus hydroxyl ion has negative charge. Characteristics of acid. First, acid turns blue litmus paper red. Second, acid tastes sour. Third, can burn skin.
There are 6 common acids. Sulfuric acid is also called battery acid or electrolyte. Nitric acid is used to make fertilizers and explosives. Phosphoric acid serves as acidic fruit-like flavoring. Hydrochloric acid is a stomach acid. It is secreted by the stomach. Acetic acid can be found in vinegar and carbonic acid can be found in carbonated water. Strong versus weak acids. Strong acid ionize or break into cations and anions almost completely and conduct electricity well. Examples are nitric acid, hydrochloric acid, sulfuric acid, and perchloric acid.
Weak acids is an acid that partially dissociates into its ions in an aqueous solution or water. In short, do not completely ionize. Examples of weak acids: acetic acid with chemical formula of CH3COOH. B. Acetic acid with chemical formula of C6H8O7. What are bases? Substances that form hydroxide ions, OH negative ions when in water or accept H positive ions. In the picture, we see when hydrogen chloride dissolves in water, a hydronium ion and chloride ion are produced.
Here are the common bases and their uses. Aluminum hydroxide, used in color fast fabrics, antacid, water purification as shown in figure 13. It is a sticky gel that collects suspended clay and dirt particles on its surface. Calcium hydroxide, used in leather making, mortar, and plaster to lessen acidity of soil, is called caustic lime. Magnesium hydroxide, used in laxative and antacid, is called milk of magnesia when in water. Sodium hydroxide, used to make soap, oven cleaner, drain cleaner, textiles, and paper, is called lye, and caustic soda generates heat exothermic when combined with water, reacts with metals to form hydrogen. Ammonia is used in cleaners, fertilizer to make rayon and nylon. It has irritating odor that is damaging to nasal passages and lungs. Characteristics of bases: taste bitter, slippery. Bases turn red litmus paper into blue, can burn skin. Strong versus weak bases. Strong bases ionize, break into cations and anions almost completely and conduct electricity well. The examples are potassium hydroxide and sodium hydroxide. Weak bases do not completely ionize. The example is the ammonia. Review. Acid, a solution that has an excess of H plus ions. It comes from the Latin word acidus that means sharp or sour. Base, a solution that has an excess of OH negative ions. Another word for base is alkali. Aqueous, a solution that is mainly water. Think about the word aquarium. Aqua means water.
Why is a substance neutral? A substance is neutral when 1. It does not ionize at all, therefore no hydrogen or hydroxide ions. 2. It has equal concentration or amounts of hydrogen and hydroxide ions. How acidic or basic is it? pH measures the concentration of hydronium ions. The concentration of a solution is a measure of how crowded the solid particles are. The more crowded, the more concentrated. It is critical to certain processes and functions. Examples are enzymes and blood. pH indicates the hydronium and hydroxide concentration. The more concentrated, the more particles are.
Concentration versus strength. Concentration is not the same as strength. Concentration deals with the amount of hydronium ions in the solution compared to the amount of water in the solution. More acid or base and less water is equals to more concentrated. More ions and less molecules is equals to stronger. How acidic or basic is it? pH scale of 0 to 4, it indicates concentration of hydronium ions. 0 to 6 is equals to acid. When it is closer to 0, it is more acidic. 8 to 14 is equals to base. When it is closer to 14, it is more basic. 7 is equals to neutral. H3O plus concentration is equals to OH minus sign concentration. To determine whether a substance is an acid or a base, before and after the reaction, count the hydrogens on each substance. If the number of hydrogens decreases, the substance is the acid. Donates ions of hydrogen. If the number of hydrogen has increased, the substance is the basis, accepts ions of hydrogen.
How acidic or basic is it? The HPH unit is equal to a power of 10. Example, pH 3 is 100 times more acidic than pH 5. Review. Strong acid, an acid that has a very low pH of 0 to 4. Strong base, a base that has a very high pH of 10 to 14. Weak acid, an acid that only partially ionizes in an aqueous solution. That means not every molecule breaks apart. They usually have a pH close to 7 of 3 to 6. Weak base, a base that only partially ionizes in an aqueous solution. That means not every molecule breaks apart. They usually have a pH close to 7, 8 to 10. Neutral, a solution that has a pH of 7. It is neither 20 acidic nor basic.